Hello and welcome to video 2 on transition metal complexes. In the first video, I walked through how we get from a molecular formula to a three-dimensional structure of a transition metal complex. And today, I will use our three-dimensional structures to get to metal oxidation state. So we'll focus on the metal and think about, oh, what's the charge on that central metal atom or ion? And furthermore, once we know the metal oxidation state, we can also determine the number of electrons that occupy the valence d orbitals in that transition metal complex. And I'll talk more about this when we get there. So the kind of key equation for determining metal oxidation state, or the key relationship, is to recognize that the overall charge of the complex is equal to the charge on the ligands plus the charge of the metals. And that kind of makes sense, that the charge of the whole is determined by the charge on the thing stuck to the metal plus the charge of the metal itself. And so one thing we can say is that metal oxidation state is, you can really think of as the metal charge, but oxidation state is kind of the technical word we use for it. And so I'll show you how we think about this, starting with complex 1 here. So we have this cobalt complex. First, thinking about complex charge, like what is the charge on this complex? That's kind of the charge that sits outside the square brackets. It's, I didn't turn anything on. It's this. The complex charge is equal to +1 in this case, because that's the overall charge of the full complex. We don't know how much of that +1 charge comes from the metal versus how much comes from the ligands, and so that's kind of the other thing we need to figure out now. And so if we want to think about the ligands, the ligand charge, and I am going to just kind of rewrite this because I think it's helpful the first time. Right, so metal oxidation state, this one is what we're trying to figure out. Right, this one is what we're trying to figure out. So the thing we need to evaluate is the ligand charge. How do we think about ligand charge? And so when we talk about charge on the free ligands, what we mean, what we're actually doing, is we're kind of imagining that we draw a resonance structure where we take the electrons in the metal ligand bond and give them to the ligand. So the free ligand means the ligand not attached to the metal. We want to think about its charge. What we're really doing is we're imagining, hey, let's pretend that the metal ligand bond breaks, and then that ligand is no longer bonded to the metal, and we've given the ligand the 2 electrons that once were part of that metal ligand bond. And we ask the question, what is the charge of the ligand? We can do this for every single ligand. And so, for example, like, we can do that one. And that gets us to that chloride, right? Every chloride will be the same. We can also do it for ammonia, which will get us here. And all the other ammonias, that's true as well. You don't have to draw this really funky resonance structure. I do mean for this to give you an idea of like what's the mental exercise we're doing. When we talk about figuring out the free ligand charge, what we're doing is we're saying, let's pretend that the ligand takes the electrons from its metal ligand bond and then assign the charge. So what is the charge on these ligands? And so you could do this by assigning formal charge. You also can just go look at our handy-dandy ligand table. And so I'm going to scroll up and say, okay, let's start by thinking about like the Cl, right? It turns out that Cl ligand is one of the ones in table 23.3 from Klein, and it says like, hey, Cl is generally a minus ligand. So it's kind of telling us like, oh, it should be minus. We can actually confirm this. We can assign the formal charge to this chlorine. And in fact, Cl minus is, I'm actually going to redraw it here just to help me keep track. I'm going to redraw all of these ligands here just to have the complete listing, right? If I want to think about the total ligand charge, I've got 2 chlorines and 4 nitrogens. And what I just said is, hey, this is negative, and this is negative. If I assign formal charge, I can see it's negative. I can also look it up in my ligand table. It's negative. I do the same thing with ammonia. So if I want to look at ammonia, NH3, I can similarly, and I guess I can put that charges here too, just for giggles. I can similarly go up to my table and say, oh, like that NH3, that ammonia, I should talk about that last time, like that's this one right here. That one is neutral and uncharged, right? In the chloride case, there's like the clear negative charge. In the ammonia case, there is no charge. And if we wanted to confirm this, right, we could draw out the Lewis structure of that and see that indeed there is no charge. For any of these. So what is the total ligand charge? The total ligand charge is the sum of all these, and it equals -2. -1 from the first chlorine and -2 from the second chlorine. And the ammonias contribute nothing. So we end up kind of with this equation that says, all right, the overall complex charge is +1. And that's equal to the ligand charge, which is the sum of the charges of all the free ligands. That's equal to -2. Plus oxidation state of the metal. And I can then move that -2 to the other side of the equation, and I can say that +3 is the oxidation state. I have cobalt 3+, or 3+ is the oxidation state. That's kind of 2 ways to say the same thing, right? And so another, yeah, so that's kind of what this is saying, and I guess I can kind of draw, like what I've basically concluded is that the metal oxidation state is +3, the overall ligand charge is -2, and how do those two things play with each other? Well, if I have a +3 and a -2, that results in an overall +1 charge. And so that's kind of how all these different charges play with each other. All right, the second part is that once I know that I have cobalt +3, I can ask, how many electrons are there in the valence d orbitals of this cobalt 3+ complex that I've drawn? And the valence d orbitals in this case are because it's the 3d orbitals for cobalt. I can kind of show you that up here, right? Cobalt is right there, right? It's in a row where the 3d are the valence d orbitals. If I were doing, say, rhodium beneath it, then the valence d orbitals would be the 4d, and iridium would be the 5d, right? It's whatever yeah. Okay. So how many electrons are in the valence d orbitals of my cobalt 3+ complex? So the way to think about this is a cobalt 3+ complex has lost So just to make sure it's clear, like when we say we have cobalt 3+, that means that it has lost 3 electrons from if it were a neutral atom, right? So a cobalt 0 complex would have an equal number of electrons in the cobalt to the number of protons in the cobalt. A cobalt 3+ has 3 more protons than it has electrons sort of in the cobalt atom. So when we say it's 3+, what we're saying is, oh, we're taking the atomic or neutral number and subtract 3. Okay, so we need to figure out if I just had neutral cobalt, if I had a plain cobalt atom, how many valence electrons would there be? The valence electrons of cobalt, well, here's cobalt here. We can kind of count. There would be, I'll number them. There would be 1, 2, 3, 4, 5, 6, 7, right? So if I had just neutral cobalt, there'd be 7 3Ds, and there would also be 8, 9. There'd be 2 electrons in the 4 S's. These are the valence electrons. Right? In a neutral cobalt atom, there would be 9 valence electrons. And I do need to take into account both the 4s2 and the 3d7 for that. So for cobalt 3 plus, there's 6 valence electrons, because I've lost 3. And the key assumption that we make, and this is this assumption up here, whatever number of valence electrons we have, we dump them all in the d orbitals. We assume that they are all occupying the valence d orbitals. We assume that they are all in the 3d orbitals. There's 6. That is how we kind of tackle this problem. All right, so I will go through this again using the iron complex. And so once again, we can kind of do the second example with this iron complex. Once again, we need to worry about this equation of like, all right, the overall charge of the complex is equal to the ligand charge plus the metal oxidation state. The overall charge of the complex is -3 this time, right? These potassium ions are just hanging out to balance the charge. The 3- is describing the charge of the actual transition metal complex. And so we have -3 is equal to ligand charge plus metal oxidation state. Just like before. And so in this case, you have 2 options for how to go about doing this problem. You could say, oh, like I have all 4-eyed ligands, F ligands. Those probably exist in direct analogy to chloride, and it turns out that all the halides, 4-eyed, chloride, bromide, iodide, they're pretty much always negative ligands on metal. And so up in our handy-dandy reference table, we have chloride. And so you could be like, oh, like 4-eyed is right above chloride, and bromide and iodide are right below it. They probably all are the same, and that actually would be correct. But I want to show you the way that you can kind of figure out if you have a 3-dimensional structure of a transition metal complex, you can figure out the charge of the ligand by drawing like the funky resonance structures that I told you about. And so the funky resonance structure says, all right, we're going to take the metal ligand bond, and we're going to break it and give those electrons to the ligand. And we do that for every one of the fluorides, and they're all going to look the same. So here we are, because it's 6 of the same ligand. You can keep track of the fact that there's a 3-, right? I have done this exercise. I say, okay, take the metal ligand bond, give the 2 electrons in that bond to the ligand, and I get to this. And so I've got to evaluate. I have 6 of this in terms of evaluating the ligand charge. the formal charge analysis tells me that this fluoride is negatively charged. The valence number is 7. There are 8 free electrons around it. 7 minus 8 is -1. And so the overall ligand charge the total ligand charge is -6 because each fluoride contributes -1, and there's 6 of them. So that lets me rewrite my equation. And I get -3 is equal to -6 plus the metal oxidation state. I then can move my -6 to the other side, and I get +3 is equal to the metal oxidation state. So I have iron 3+. Just like I had cobalt 3+ earlier, right? So the cool thing is, this is a complex with an overall charge of 3- with a metal 3+ in the middle. Before, I had a complex with an overall charge of plus, but it also had a metal 3+ in the middle. And it's because the ligands are different that I get those different answers. All right. I can then kind of do the same thing where I can figure out the number of d electrons. If Fe0 the number of valence electrons would equal some number, right? And we have to go to the periodic table to figure that out. So back to the periodic table. I'm going to need to erase all of my counting on here so that we can see. Where is iron? There's iron. How many valence electrons does it have? Well, I got 1, 2, 3, 4, 5, 6, 7, 8. Because again, I'm taking into account both the 4s and the 3d. I'm taking into account every kind of electron that makes up that valence row. So there would be 8 valence electrons if I had iron 0. Iron 3+ has 5 valence electrons, and so I have 5 electrons in those valence 3d orbitals. All right, we can keep going. One more example for you, and of course I encourage you to pause this to see if you can do it yourself. In the platinum case, we have actually something that's pretty similar to cisplatin in a lot of ways, but I just want to remember what I'm saying. In the platinum case, my overall complex charge is 0. There's actually no net charge on this, right? There's no square bracket, there's no charge. But I still have to worry about ligand and metal oxidation state. I could once again draw my resonance structure where I break the metal ligand bonds and actually assign formal charges to the atoms. Or I could go look up these ligands in my ligand table. Maybe this time I'll go look up these ligands in my ligand table. The ligands that I have are a pair of CN ligands and this ligand here, which is ethylene diamine. Let's head up and see if we can find the CN ligand and see if we can find ethylene diamine. Here's CN. We talked about it last time. And CN is a minus ligand. I'm just going to go record that. I have 2 CN minus ligands. I also have the ethylene diamine ligand, this one here, and this one is neutral. There is no charge on it. So the overall ligand charge is equal to -2. I can then move this to this equation and say, plus 2 is equal to my metal oxidation state. And so that means that I have a platinum 2+ compound, platinum 0, the ground state electron configuration would be, here's platinum, so I got to count. I got 1, 2, 3, 4, 5, 7, 8, 9, 10. Right? If I had a platinum 0, that would have 10 valence electron. 10? Did I count that wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that's right. The fact that this is not blue confused me for a second. Okay, so if I had platinum 0, I would have 10 valence electrons. For platinum 2+, I lose 2, so there's 8 valence electrons, and that has 8 electrons in the 5d orbitals, right? Because platinum is 2 rows down, it's in the 5d row. And that is all I got.